On 15, we have a bit of a booger. We have a fast equilibrium, the same fast equilibrium, and a slow step. Now, the slow step is also the rate determining step. The real test writers really like that phrase, rate determining step, so they will spell it out. So what's the rate law? Well, this is one with a bit of a trick to it. Now, for any elementary step, you can look at the given equation and write the rate law. So the step 1 and 2, we don't exactly have a rate law, we have a fast equilibrium. And here's the idea. If these are faster, yet they pour their C product into step 3, C is being produced faster than 2 can use it up, because these are faster than the slow. Therefore, the amount of C builds up, and we get an equilibrium. The C builds up and starts falling apart back into A and B. So these are going to form an equilibrium, and they might not tell you that. You might need to realize that. The test writers may not say the word equilibrium. They just may say that this is the rate determining step, and you need to know that that's the slow step, and therefore the other two are the fast ones. So this is the rate determining step. What would the rate law be for step 3? The rate law would be rate equals K times C to the second power, because there's a 2 there. And the coefficient becomes the exponent. Now, what do we know about equilibriums? We know that equilibriums can be expressed in terms of their K or their Kc or Keq. Maybe we'll put Keq. It doesn't exactly matter if you label it K of equilibrium, or if we're using molarity here, then K of concentration. Those are really kind of the same thing. Ask your teacher. And what we know is a phrase that, at least the way it was taught to me, I have just said it about 1,000 times now. K will be equal to products over reactants to the power of the number in front. I would chant that 50 times, and that might not be a joke. Products over reactants to the power of the number in front. Product, and we mean molarity, or pressure for a gas maybe, but these aren't gases, we assume, over reactants, rated in molarity, to the power of the number in front. Everything is in the power to the number in front, which is 1. The coefficients here are 1, and so the exponents here are all 1. Now, here's the problem. Here's the thing. We, as the reaction designers and the people putting the stuff in the beaker, are not putting in any C. We put in A and B, and it created C. They don't have to happen in series, they happen in parallel. While this one's happening, that one's happening. So the rate of delivery of C is effectively the rate of either one individually. The rate of the delivery of C to step 3 is the rate of either one, because they're both happening at the same time, so they're delivering C at the same rate. But I can't just leave step 3's rate in terms of C, because I don't know what that is. That's not a reactant. C is an intermediate, and that's not fair. You can't leave an intermediate in a rate law. We want it in terms of reactants that we supply. So let's substitute in mathematically for C. I know that C can be expressed this way, and if I solve for C, I get it equals K times AB. So I can take KAB and put it in for C, which means I get this amount, because this substitutes in for a C, quantity squared. So we get to square all 3 things. A squared is A squared, B squared is B squared, and the part that kids sometimes have trouble with is saying, but you didn't square K. Well, I did in this way. K is a certain number, and I don't know what it is, but if I square it, it's yet another very certain number. I mean, if you told me this was 3, I'd say, okay, it's 9. If you told me it's 5, I'd say, okay, it's 25. If K is 5 and I square it, the answer had better be 25 when you get done right there, right? So I don't know what K is, but its answer of being squared is a very definite number. And if I take that squared and multiply it by another very definite number, which you just look up or they would tell you or something, then that answer is yet in a third very definite number. It's not in question once you discover what these 2 numbers are. That number is the same, and it will remain the same for this reaction, period. So the rate overall will be this K squared times that K, which gives another K, times A squared times B squared.